Thank you, Vast and University of Pisa. We have Lovell from Los Alamos National Labs presenting. If you were able to come to the OpenCHAMI tutorial yesterday, you would have seen some of his presentations, and today he's going to talk a little bit more about it for AI systems and reflections of OpenCHAMI over the first year. He's going to be joining us over Zoom. In fact, I see him now.
So I have to request?
So we're going to leave, yeah. So Alex, take it away.
Thank you. You guys can hear me okay?
Yes.
All right. I'm really sorry I couldn't be there in person. I was looking forward to seeing so many of you, and it just didn't work out this year. So hopefully I'll be able to see you someplace else sometime soon. Get things arranged here. Speaking of which, if you happen to be in London the first week in May, we're holding a dev summit. So after the talk, I'll be happy to help folks get involved there. All right, let's get moving. So, good morning. I guess it's still morning there. My name is Lovell. I'm an HPC architect at Los Alamos National Laboratory. I want to share a story today about a pair of AI systems at LANL. It's a story about a leap of faith to put our open source software into production quickly, but it's also a story about the people who made it happen, the challenges they faced, and the changes we're seeing at LANL as a result. Along the way, I'm going to introduce you to OpenCHAMI because some of you I know haven't seen it before, and the story doesn't really make sense without it. For those of you who do know OpenCHAMI, there are plenty of new details that I haven't shared anywhere else. You're going to hear about the operations that OpenCHAMI made possible for us, the benefits to our users. Let's start with a decision. About a year and a half ago, our scientists really leaned into large language models as research tools. Not toys or experiments, but real research tools. They'd been using AI previously, but developments in the broader ecosystem opened up further opportunities for them. Like many other sites, LLMs became ubiquitous, seemingly overnight. Our existing GPU capacity was already heavily used and quickly became overwhelmingly oversubscribed. We needed more capacity fast. Our funding programs allocated budget, and we started talking to vendors. We landed on Dell to deliver on a tight schedule, 2 systems, one with 4 nodes, one with 10. Different security environments, different user communities, same underlying architecture. Now here's the first real decision point for us. When you buy an AI system today, you have choices. You can buy the DGX version, fully integrated with management software bundled and ready to go out of the box. Or you can buy the HGX version, the same NVIDIA GPU hardware, but without the bundled software stack. HGX costs less, meaningfully less. We wanted to spend our budget on GPUs, not integration. So we chose HGX. And that meant we needed a management solution. HGX doesn't come with one. Obviously, we chose OpenCHAMI for the task. We'd already used it for a handful of test systems and had picked a different first system, a different first production system for later in the year. But the opportunity presented itself, and we'd earned the confidence of people making decisions. We had a backup plan, of course. I mean, we always have a backup plan. In this case, we never needed it. Before I go further, let me spend a few minutes on OpenCHAMI itself, because not everyone in this room has seen it. If you have, this will go fast, and I promise there's new material on the other side. OpenCHAMI is an open source HPC system management framework, and it is also the community that guides its development. The founding partners are Los Alamos, HPE, NERSC, the University of Bristol, and CSCS. Dell joined us later. We have about 24 active committers across 6 sites, and we're growing. The core idea is this. Most of us have gained some cloud experience, and cloud changed how we think about infrastructure. In the cloud, you declare what you want, and it appears. If something breaks, you tear it down and you try again. That's a very powerful mental model for infrastructure. But HPC operators aren't cloud engineers. They're managing relatively fixed systems that are supposed to run reliably for the life of the machine, sometimes just on one or two sets of jobs. They want to touch these things as little as possible, and they don't have spare capacity to experiment with. OpenCHAMI lives in the gap between those worlds. Cloud ergonomics, declarative, idempotent, API first, on bare metal at scale with specialty interconnects. And with a focus on the experience for the sysadmins and operators who are ultimately responsible for the uptime of the machines. That's the motivation for the community. Now let me show you how it actually works. The model we use is called the OODA loop, Observe, Orient, Decide, Act. It's a strategy concept, and you may know it by different names, but it describes exactly how good system management should work. You look at reality, you decide what direction you want to go, you figure out what needs to change, you act, and then you loop around and investigate the new reality. If you've used Kubernetes, you know this pattern. Kubernetes is a giant control loop that is always asking, what's the desired state? What's the actual state? What do I have to do to close the gap? So we love that idea, but we wanted it with fewer moving pieces, less complexity, and faster reconciliation. In OpenCHAMI, observe means querying your BMCs through Redfish, serial numbers, GPU counts, firmware versions, that kind of thing. With sensible updates and caching, you can make very good automated decisions. The serial numbers shouldn't be changing from minute to minute, but the power state might. Orient means you declare how you want to slice that hardware into groups. You declare intent. Decide means the system figures out where reality differs from your intent. Act means applying the changes. For OpenCHAMI, that means executing REST calls and rebooting machines. The key insight, and this is the thing that makes cloud feel magic, is that you can rerun it safely until reality matches intent. That's what we mean by cloud ergonomics for bare metal. And we built with a philosophy in mind. John Gall wrote this in 1975. A complex system that works is invariably found to have evolved from a simple system that works. A complex system designed from scratch never works and cannot be made to work. Dr. Gall may have underestimated the will of a sysadmin to make a complex system work when users are depending on it. We took his advice anyway. The default in OpenCHAMI is the simplest thing that works. No stateless systems, no persistent database, no required authentication, no required containerization. You opt into complexity as you need it. For a single purpose cluster, you can be running in under an hour. Starting with simplicity in mind guides a lot of what we do, and I think accounts for some of our success. I'll talk about those later. You can think of OpenCHAMI as a slider that takes you from a simple cluster to one with dynamic complexity. Add services as you need them. Enable features when they help you better support your users. Make the tooling fit your site, not the other way around. Here's the architecture at a glance. I'll move through it quickly for the folks who've seen it, but I want to make sure everybody is on the same page. As you can see, there are three actors here. The first is you, or your automation, which describes intent. The second is the OpenCHAMI control plane, which allows you to express your intent and apply it everywhere. The third is your hardware. Discovery talks to your BMCs through Redfish, SMD holds your inventory, BSS composes bespoke boot scripts, and our metadata service handles CloudInit on demand. Every node gets exactly what it needs. Everything flows through REST APIs. Every action is auditable, no magic shell scripts, no tribal knowledge baked into files that only one person understands. And here's the part that becomes very relevant in a few minutes. Up until the point of actual boot, nothing has changed on the hardware. Everything is text files, everything you can check into version control, pre-process, and validate for syntax and test. That's the architecture as it runs in production today. Before I go further, I want to spend a moment on CloudInit because not everyone has encountered it, and it's doing real work in this architecture. Cloud Init is an industry standard for first boot node configuration. AWS uses it, Azure uses it, Google Cloud uses it. It's embedded in OpenStack and many other private clouds as well. If you've ever launched a VM and had it come up with your SSH key already installed and your hostname already set, that was Cloud Init. The idea is simple. The node boots, the kernel loads, and before anything else happens, Cloud Init reaches out to a metadata service and asks, what do I need to become? The metadata service, in our case, OpenCHAMI's, answers based on which groups that node belongs to. It says, install these packages, write these config files, load this munch key, register with this Slurm controller. And it runs once, it runs fast. Because it's pulling from OpenCHAMI's group-based config, every node gets exactly what its role requires, not a generic image with manual post-processing on top. That's what gets us from kernel load to job ready in about 2 minutes. Now, let me tell you what it looked like when we pointed it at our Dell HGX nodes. Meet Selene and Helios. We named our two AI systems after children of the Titans from Greek mythology, representing the divine forces of day and night. Helios drives a golden chariot across the sky, while Selene follows in a chariot pulled by white horses. They represent a balance of cosmic opposites, clarity and mystery. Naming supercomputers is a fun digression in any talk. Selene is the smaller of the two, 4 GPUs, dense with H100s. Helios is the larger 10-node system. Both are Dell HGX. Neither came with a management software stack. They were both designed for different security environments, different user communities. But they shared the same hardware, same architecture, same firmware baseline, and as it turned out, the same management strategy. Our plan was originally to have over a month from delivery to handoff. This was to be our first time with OpenCHAMI on Dell hardware, our first time with production change control, our first time dealing with multiple security environments. We were more worried about the processes than the software and needed time to get familiar with the hardware. Time to work through any surprises, time to do things properly. We got 2 weeks. By the time the hardware was delivered, we had 2 weeks before users needed to be on the system for their own deadlines. Earlier, I talked about the OODA loop, observe, orient, decide, act, and how OpenCHAMI brings that control loop to bare metal. Here's something I didn't say then. The OODA loop only works if your feedback is fast. If it takes 3 days to observe the consequences of an action, your loop runs 3 days slow. You're always reacting to last week's reality. This is a core problem with traditional HPC system administration. The loop exists, admins are the ones who observe, orient, decide, and act, but the cycle time is measured in days or weeks. Hardware changes are really expensive. Image rebuilds take hours. Validation means rebooting production nodes. When the loop is that slow, you stop running it. You make changes as rarely as possible, and you rely on institutional knowledge instead of well-tested runbooks. And when something breaks, you're debugging blind. What we've been moving toward is shortening that loop, and the way you shorten it is pipelines. Build the image, test it, validate it in an environment that looks enough like production. Know that it works before you touch a production node. That's a software development idea, CI/CD, pipeline-based delivery, and it turns out to work extremely well for system images and boot configurations. OpenCHAMI's API-first architecture makes this possible. When everything is an API call and everything is a text file, you can automate it, version it, and test it in isolation. You can run your OODA loop in a pipeline before you ever affect a user. With Helios and Selene, our team gained OpenCHAMI tools to apply DevOps principles to HPC deployment. That DevOps mindset paid off. We didn't wait for the hardware to get started. Dell was able to tell us ahead of time exactly what firmware revision the BMCs would have when the systems arrived. So we found other Dell hardware on site at the same firmware level and started testing OpenCHAMI against that. Not against the actual HGX nodes, against the same BMC software though. Same API surface, same behavior. At least we thought so. By the time Selene and Helios hit the floor, we already knew how OpenCHAMI would talk to them. We'd already built and tested system images with the drivers and software we expected to be needed. We'd already found and fixed a handful of edge cases. We'd already written the runbooks. That runbook work came out of something else we'd been building separately, a summer intern program we call the Supercomputer Institute. That Supercomputer Institute is our summer intern program at LANL. We take students, many of them with limited HPC experience, and we teach them to build and deploy systems from scratch. SI, as we often call it, predates OpenCHAMI. But over the last few years, it has been a proving ground for our software and a great bug shakedown. The byproduct of that program is documentation. Real documentation written by people who didn't already know the answer and had to figure it out. And that's the best kind. I also need to clarify that our SI students don't just build clusters, they plan projects to use them. In the past few years, some students have chosen projects to improve OpenCHAMI. We had one student work on installing the OpenCHAMI containers on a network switch, removing the need for a head node completely. Another did some innovative work on using TPMs with OpenCHAMI to improve security. Yet another built a proof of concept for our ultra-fast switching from Slurm images to Kubernetes images using kexec. More on that in a bit. The runbooks that came out of the Supercomputer Institute became the foundation for our Selene and Helios deployments. Clear, step-by-step, written for someone who's doing it for the first time. Which, when it comes to Dell HGX hardware running OpenCHAMI, everyone was doing it for the first time. We also used the time before delivery to build and test bootable system images. Our target OS as a container, assembled with our image builder, tested on other non-HGX hardware. Working with the system image as a container allowed our team to run lots of tests without occupying real hardware. We couldn't validate GPU drivers without any GPUs, but we could test most everything else. When the hardware arrived, we had runbooks, we had tested images, and we had already validated the BMC configuration patterns. We were ready. We were very ready. The hardware arrived and our timeline compressed almost immediately. Instead of a month, like I said, we only had 2 weeks before users needed to be running jobs to meet their research goals. And this is where the staffing situation got interesting. Our main sysadmin team wasn't available. They had other priorities, real ones, that kind of thing happens. What we had was 2 sysadmins, 2 students, and 2 hardware techs. That's not the team you draw up on a whiteboard for a compressed critical deployment. But here's what happened. The initial OpenCHAMI installation on Helios took 1 or 2 days. Let me put that in context. This is hardware none of us had ever managed before. Dell HGX, iDRAC BMCs. A completely new node architecture for OpenCHAMI. And we were up and running in 2 days. Because the runbooks were good, because the system is designed to be simple by default, because our pre-delivery testing meant we already knew how to talk to those BMCs. Now, we did hit cabling issues, physical connectivity problems that had nothing to do with software. That troubleshooting took a few days. But within just over a week of the hardware arriving on the floor, Helios's 10 nodes were turned over to the scheduler. Early users were able to run jobs. Then we started on Selene. Selene took us 3 days. 3 days from start to scheduler handoff of our 4-node HGX system. What changed? We'd done it once. The runbooks got refined. The team knew what to expect. The images were already tested. The BMC configuration patterns were already validated. OpenCHAMI's architecture made the second deployment feel like running the same play twice instead of learning a new sport. And I should point out that much of the 3 days was spent on non-software processes, like change control board and access requests. If we were only counting sysadmin time on the hardware, LANL was ready in an afternoon. That repeatability is not an accident. It's a design goal. We relearned the power of good documentation through our SI runbooks. Our pipelines allow the team to safely test without affecting real users. Code contributions from the implementation team made everyone's life easier. Other teams gained agency from the new DevOps workflows without sacrificing safety. Spend your work time in the build, test, and validate side so that deploy is unremarkable. Now I want to talk about the team, because I think this was the part of the story that surprised us the most. 2 sysadmins, 2 students, 2 hardware techs. The sysadmins did some of the early OpenCHAMI work, but transitioned to supervisory roles as the rest of the team got going. We even dropped down to 1 sysadmin for the second deployment. One of our hardware techs was delivering mail a year earlier. He signed up for a job to rack hardware and replace plumbing. Both the students were finishing their undergraduate degrees just a few months earlier. These are not the people you would put on your most critical deployment when you have options. So we gave this team the good documentation, a well-designed system, and enough supervision. They felt safe iterating, knowing that each iteration could be checked before it went live, and the cost of experimentation was low. And they delivered. They not just delivered, they exceeded. They filed bug reports against OpenCHAMI when they found rough edges. They made code contributions. They improved the system for everyone who would come after them. They didn't just use the tool, they became part of the project. And when it came time to add another cabinet of nodes, this time from HPE, they didn't even bat an eye. For them, integrating a hybrid cluster 1 cabinet at a time seemed straightforward. When it came time for our first designated system time, DST, our scheduled window for firmware upgrades and security patches, they didn't wait to be told what to do. They planned it themselves. They wrote the change plan. They coordinated the steps. They ran it with limited oversight. Now, DSTs in our world typically mean long days, and users know this. When we have a DST scheduled, our user-facing testers, they come in late because they expect to be there well past normal business hours. On our first DST for LANL, we were done before those testers arrived in the office. That's what good tooling does for a team. It takes the ceiling off their performance. So that's the deployment story. Let me spend some time on what the first year taught us. When we bought LANL and Helios, we were thinking about provisioning. How do we boot these things and how do we manage them? A year in, we're thinking in terms of something different. We're building pipelines and going beyond with more DevOps concepts. Our team has started planning what they call a release train for our systems. The idea is straightforward. The most recent image to pass all the tests is the new release at a certain time. Even with our more traditional systems, we've got several sets of teams that are all trying to improve the user experience at once. There are constant change sets coming from different areas of our HPC center. Our file systems team wants a new kernel parameter or a new module. Our security team wants a set of patched RPMs. Our monitoring team wants just one more metric. Before we started thinking in DevOps terms, the sysadmins would be on the hook for merging all of these changes in time for the next DST. With our release train, each of these teams can integrate their own changes and get near instant feedback. A new system image goes through testing pipeline, automated tests, validations, sign-off. When it passes, it goes live, almost automatically, on a scheduled day at a scheduled time. Very little manual intervention, certainly no all-hands war room, no heroics needed. Users get notified that they have a choice: upgrade their nodes immediately, or wait for running jobs to finish and then upgrade. This is how software companies ship code. This is DevOps thinking applied to bare metal HPC nodes. A year ago, this team was figuring out how to cable a BMC. Now they're designing CI/CD pipelines for a supercomputer. And that's not a small shift. One of the harder problems with AI systems is that they serve two masters. HPC scientists want Slurm. Kubernetes is essential for containerized workloads. And those two schedulers don't play well together. The traditional answer is pick one, or buy two separate systems and manage them separately. Of course, there are some projects that add support to Kubernetes for running Slurm jobs and vice versa, all with some trade-offs on complexity and tooling. With OpenCHAMI, we have another option. We can run completely different system images on different nodes, a Slurm image on some, a Kubernetes image on others, and we can change the composition with a minimal set of API calls. Want to shift from 10% Kubernetes to 90% Kubernetes? That's a configuration change, not a project. Want to flip it back? It's the same thing. We're doing this manually today. The release train work is going to make it more automatic, but even manually, the ability to rebalance a cluster between schedulers in minutes rather than days is a genuine operational superpower. Here's one more thing we figured out in year one. We don't like rebooting. I know we're the only ones. Not because reboots are hard, of course, but because reboots are incredibly slow. Power on self-test on an HGX node can take 20 minutes. Time that users aren't running jobs, time that we're paying for and not getting value from. So we started using kexec. If you're not familiar with kexec, it's a Linux kernel feature that lets the running kernel load and execute a new kernel directly without going through post. The system doesn't power cycle, it doesn't go through BIOS, the new kernel just replaces the old one. We integrated kexec with BSS, OpenCHAMI's boot script service. When a node needs to take a new image, it asks BSS what its current boot configuration should be. BSS computes it on the fly based on the node's current groups and configuration intent. The node loads that configuration and then kexec reboots. The whole thing takes under a minute. So that's not under a minute to schedule, that's not under a minute to initiate, that's under a minute wall clock from I want a new image to the new image is running. This is the kind of thing that only works when your boot configuration is fully computed by a service and not baked into static files. OpenCHAMI's architecture made it straightforward. In a traditional provisioning system, this would be a significant engineering project. So let me tell you where OpenCHAMI stands today, because some of you are going to go home and try it. At least I hope so. OpenCHAMI is deployed on 7 supported platforms at LANL and other places around the world. Approximately 24 active committers across like 6 sites. The core workflows, bootstrap, discovery, grouping, configure, boot, they're all production ready, they're all stable. We're actively replacing the original Cray Shasta components with API compatible services we built ourselves. That transition is well underway. Legacy APIs are preserved while new features are enabled. Each microservice is more consistent with the whole and easier to test and validate in isolation. Coming up next, we're going to add node-centric boot orchestration. We're going to add real secret management and a cell-based stateful architecture. One small OpenCHAMI instance per cabinet will be possible. So an upgrade gone wrong affects one cell and not the whole cluster. And although it's not on the official slide here, but very relevant to the folks in this room, where we're experimenting with agentic workflows. OpenCHAMI's API-first model is naturally suited to LLM integration. We're not handing an LLM the keys to the cluster today. I don't want to vibe code a supercomputer. But we know that that time is coming, and we want the API surface area to be ready for it. OpenCHAMI is a genuinely open project. All TSC meetings are public. Roadmap issues are public. Our request for discussion model means the community shapes direction before decisions are made. So you can get involved. Browse our open pull requests, pick an issue, join an RFD discussion, attend our weekly office hours. All of it is on our public calendar, and you can find it at openchami.org or github.com/openchami. Let me close with the thing I want you to remember. We bought 2 AI systems with no management software bundled. We tested against the hardware before it arrived. We handed the deployment to a team of students and hardware techs with good documentation and a well-designed system. They turned over nodes in a week. They completed our first DST before our testers even got to the office. Then they filed the bug reports, they made the code contributions, and they started designing CI/CD pipelines for a supercomputer. That's not a story about exceptional people, although I'm pretty proud of them. They felt safe using the system, understanding where it would protect them and where extra caution was necessary. It's a story about what happens when the tooling is simple enough to be understood, documented well enough to be followed, and open enough to be improved by the people using it. If you're thinking about an AI system, or any system, and you're weighing your options for management software, I'd like you to give OpenCHAMI an afternoon. The URL is openchami.org, and you can find our Getting Started guide right there. It's designed to get you to a working first boot in an afternoon. If you hit a wall, come find me. I encourage you to join our Slack and ask any of our contributors, but you can always rely on me. Thank you for inviting me to speak, and thank you for your kind attention. I'm happy to take as many questions as time allows.
All right, thank you, Alex. Okay, we have a question here. So we're going to have a fun experiment here. So try to keep the questions brief because Hussein has to repeat it to him over the laptop. And Hussein's memory these days, it's like...
Okay.
Hi, thanks for the talk. I'll condense as much as possible. You use the parallel between OpenCHAMI and Kubernetes several times over. And in my experience, Kubernetes is good for Google-sized stuff, but most of the world is not Google. So I warmly favor simpler solutions such as Docker Swarm. So is OpenCHAMI more of a Kubernetes or more of a Docker Swarm?
You're screwed, Hussein.
Yeah, I think I heard the question. I think I can hear the room pretty well. So I think it's better to think about the reconciliation loop from Kubernetes without thinking of all the complexity of Kubernetes when thinking about OpenCHAMI, because that was explicitly our goal. We don't want our HPC sysadmins to have to be Kubernetes experts before they can start providing HPC services. So Docker Swarm is probably a better comparison. We are informed by the idea of the control loop, but we don't want all those moving pieces. We don't want to maintain several etcd clusters. We don't want to have to think about all of the custom resource definitions and the ingresses and all of those things. So that's part of why we did not use Kubernetes and base OpenCHAMI on Kubernetes. We instead based it on something much simpler. So I hope that helps.
Any other questions? You got one?
Great. So I'm wondering if you can give us some, updates about that too, so the audience here could have an idea about the roadmap and where we are going with the versions. Thank you.
Yeah. So the project doesn't have a roadmap in the same way that a vendor provided piece of software would have a roadmap. That would require that we had developers that were being paid in a long-term way outside of Los Alamos. But what I can tell you is that at Los Alamos, we have a set of things that we have committed to do within this year. And I know that those things are going to get done. If you go to our GitHub, you can find a roadmap repository, which has all of the lists of things that people would like. Some things are very specific. I think Dell has some very specific ideas about how they want future systems to work, and they're contributing to those. But I think for us, it's high availability. At LANL, it's high availability, which may or may not mean horizontal scalability. It might mean, failover. We're trying to put things inside Kubernetes to have them work better. That's a NERSC priority, and we think we're all going to benefit from that. We're also looking at the cell-based architecture. We found that in cloud, having lots of little cells that each update independently means that you can roll out a change to a small subset without affecting the whole. And we've already tested that with running 6 instances of OpenCHAMI for a large cluster. The other thing we're doing is adding more of the API features that make LLMs happy. And if you come to the Developer Summit in London, we're going to spend a full day talking about the future of OpenCHAMI with AI.
Thank you very much. Thank you very much. I think with this question, I think we can close it here. Please join me to thank Alex for this presentation. Thank you, and we'll see you soon.
Thank you. See you.